So welcome to this lecture. So we have been discussing the forced vibration of single degree of freedom system. We have already discussed the forced vibration due to the uh, function, harmonic force function. Forced vibration due to the rotating unbalance in the machines, the support excitations. So today we will discuss some numerical problems, okay, that are some specific problems that I would like to discuss to you. So let's start with the first problem. So this first problem, so there is a helicopter uh, rotor. So the tail rotor of section of a helicopter that consists of four blades. So there is a tail rotor of helicopter and there are four blades, each of mass 2.3 kg. So the blades has a mass of 2.3 kg and an engine box of mass 28.5 kg, and there is a engine box with mass 28.5 kg. The center of gravity of each blade is 170 mm from the rotational axis. So here we see that the blades are connected to the rotational axis and they are rotating about that axis, but their mass center of mass is 170 mm from the axis of rotation. Now this tail section is connected to the main body of the helicopter by some elastic structure, and the natural frequency of this section is 135 radian per second. So now during the flight the rotor operates at 900 rpm. Then what is the vibration amplitude of the tail section if one of the blades falls off during flight? So during the flight, when the rotor is operating with 900 rpm, one of the blades falls, and then it is asked that what will be the vibration amplitude now when there is only there are only three blades. Assume some damping ratio of 0.05. Okay. So we have, so it is clear that when there are four blades, okay, so this is my, so here are the, let's say this is, there are four blades and their center of mass is here 170 mm from the rotational axis, and this is the axis of rotation, okay, and they are rotating here. Now if one blade is fall downs, so we have like this condition, okay. So here is the center of mass. Now we can see that when we have these four blades, they are balanced because their center of mass is balanced, but if one is fall, so this one blade will be unbalanced. This blade is balanced because their combined center of mass will fall on the rotational axis, but this blade center of mass now is unbalanced after fall, before and after fall, okay. So this is a problem of rotational unbalanced mass, and so we have like, so we have the mass m equal to mass of the engine and plus mass of the blades and mass of engine is 28.5 kg, and this is 4 into 2.3 kg. So this is before, and so it comes out to be 20 37.7 kg. So this is the total mass of the system, and it is given that the natural frequency of the section, this section is 135. So omega n is 135 radian per second. So omega n equal to root k by m. So we can find the stiffness of this section. So k equal to omega n square into m, and so it is 135 square into 37.7. So that is equal to so it comes to be 6.87 into 10 power 5. This is in Newton per meter. So we have got the stiffness. Now when omega is, so omega is 900 rpm, so 900 into 2 pi by 60. So we have so 94.25 radian per second. So one blade is falling, and damping ratio zeta is given 0.05. So when one blade is fall, so we have now the mass after the falling of the blade. So m is now engine mass plus now the it is 3 into 2.3, because now we have only 3 blades. And so we have we can calculate 35.4. So this is the mass of the system. Now unbalanced mass, that is m0 equal to 2.3 kg and E equal to 170 mm. So that is 0.170 meter. Okay. So this is the mass, total mass. So and this is the unbalanced mass. This is the distance of that unbalanced center of gravity of that unbalanced mass from the axis of rotation. Now the mass is changed after the falling of the blade. The mass of the system is changed, and you know that the natural frequency omega n is equal to root k by m, and when mass is changed, definitely the natural frequency will change. Here we assume that the stiffness is not changed after falling of the blade, so we assume stiffness to be constant, but because mass is changed, now the natural frequency will be changed. So the natural frequency omega n now will be root k by m dash. So we know that k is 6.87 into 10 power 5 and m dash is 35.4. So equal to so it is 139.31 radian per second. So earlier natural frequency was 135 radian per second, and you know that it is inversely proportional to root m. So if mass is reduced, the natural frequency is increased here. Now we have to find the vibration amplitude. So we know that the vibration amplitude in case of rotating unbalance is x by m0 e by m equal to r square upon 1 minus r square whole square plus 2 zeta r whole square under root. So this is formula for x. Here m0 e, m is now here m dash, so I put here m dash. So x upon m0 is 2.3 into e is 0.17 upon m dash is 35.4 and equal to r square. So we have to calculate r, and if I calculate r equal to omega by omega n dash, and omega is 94.25 and omega n dash is 139.31. So we have 0.677. So this is r, and 2 zeta r equal to 2 into zeta is 0.05 into r is 0.677. So equal to so it is 0.0677. So we can put in this equation. So r 0.677 square upon 1 minus 0.677 square whole square plus 2 zeta r is 0.0677 whole square under root. So now we can calculate x. So we get x equal to 9.24 into 10 power minus 3 meter. So it is 9.24 millimeter. So it means that the system will vibrate with in some harmonic motion, okay, and the amplitude of that motion will be 9.24 mm. So So here we now we go for the next example. So example 2. So here in example 2 it said that when a free vibration test is run on the following system, the ratio of amplitudes on successive cycles is 2.5 to 1. Determine the response of the machine due to a rotating unbalance of magnitude 0.25 kgm when the machine operates at 2000 rpm and the damping is assumed to be viscous. So here we have a system having viscous damping. And we know that if there is a viscous damping and free vibration test is performed, so and there is some amplitude ratio. So free vibration test when we perform, so we have some amplitude ratio here decay like this. So here let us say this is x1 and this is x2. So it is given that x1 by x2 equal to 2.5. to 1, so it is 2.5. Now we have to find there is a rotating unbalance in the machine. So there is a machine of 125 kg on the cantilever beam, and the machine there is some rotating unbalance m0 into E, that is 0.25 kg into kg meter when the machine operates at 2000 rpm. So omega equal to 2000 rpm, so it is 25 by 60 radian per second, and damping is viscous. And we have given some information about the beam. So E equal to 200 into 10 power 9 Newton per meter square, and I equal to 4.5 into 10 power minus 6 meter per 4, and length of the beam is 80 centimeters, so it is 0.8 meter, and mass is 125 kg, mass of the machine. So we have to find the response of the machine due to a rotating unbalance. Okay, so we know that when we have the rotating unbalance, so there is the force m0 e omega square sin omega t on that system, and so the response x is something like x sin omega t minus phi. So this is the response. So we have to find, let's find x, the amplitude of the response. To find the response, let's first find the damping, because here we know that the logarithmic decrement delta equal to log x1 by x2, and that is equal to 2 pi zeta upon root 1 minus zeta square. So here ln x1 by x2 is 2.5 into root 1 minus zeta square equal to 2 pi zeta. So we can find 1 minus zeta square equal to, so let's calculate this. So we get from here the damping ratio, that is 0.144, and we calculate omega. So omega is 209.44 radian per second. So because we have to find the amplitude, and we know that x by m0 e by m equal to r square upon 1 minus r square whole square plus 2 zeta r whole square under root. So we know m0e, we know m because m is 125 kg. R we have to find, zeta we know, so r is equal to omega by omega n, but we don't know omega n. So what is the natural frequency of the system? So omega n equal to root k by m. M we know, but we don't know the stiffness. So now stiffness, we have a cantilever beam, so and at the end the machine is there and it is giving the transverse vibration. So we know that k for a cantilever beam is so mean we can have so this formula comes like this. So 3 ei by L cube. So 3 into E 200 into 10 power 9 to 4.5 into 10 power minus 6. L is 0.8 cube. So we get k equal to 5.27 into 10 power 6. Now we can calculate natural frequency. So natural frequency is 5.27 into 10 power 6 by 125 kg. So we get omega n 205.396. So we can get r. So we have r equal to omega by omega n. So 209.44 upon 205.396. So it is 1.02. So r is 1.02. Now we have all the things, and we can one more term. So x by m0 e is 0.25 and m is 125 kg. R is 1.02 square. So 1 minus 1.02 square whole square plus 2 into. So zeta is 0.144 into r we have 1.02 whole square and then under root. So we will get so we get here that the displacement amplitude of this system due to the unbalance of the mass is coming to be 7.02 millimeter. Okay, so I think with these examples we understand the how to identify and apply the theory of rotating unbalance in the system and find the vibration response amplitude of the system. So I thank you to you for this lecture, for attending the lecture, and let's see in some next lectures. Thank you.